1.3 limits. And before we dive in, I want to briefly introduce the concept of a limit and where the idea came from. The idea that you can approach a value without knowing the exact value. You can get a pretty good estimate by approaching it, by finding its limit. And we deal with this guy named Archimedes, who was a mathematician long, long ago. And he spent a lot of time working with circles and relating the circumference of a circle to its radius. And the formula we now know is circumference is 2 pi r. And what he wanted to do is estimate, he wanted to get actually the exact value for pi. And he did that by looking at the circle and saying, well, I can't get it directly from a circle, but a circle is kind of like a square. And so he took a square on the outside of that circle and found the upper bound for the value of pi, an estimation of pi, that is 4 units. We can see the perimeter of this square is 4 units. And he said, well, why don't I draw another square on the inside? And he got the perimeter of that square. And from that, he was able to estimate that pi fell somewhere in between 2.8 and 4. You can clearly see that the circumference, the perimeter of the circle, is less than the big square, but more than the small square. And so we have an estimate there. And he said, well, why use a square? Well, I could use a pentagon. Pentagon is closer to a representation of a circle than a square is, certainly. And so he drew a pentagon on the outside of the circle, and he drew another pentagon on the inside of a circle, and I'm sure his pictures were better than my pictures. But you can see already that the outer polygon and the inner polygon are quite a bit closer, and so the estimate of pi is going to be better already. And what he realized is that the more sides he gave his polygon, the smaller the sides became, and the closer they became to resembling a circle. As a matter of fact, a polygon can only be a polygon as long as it doesn't become a circle. Okay? So in that sense, the circle is the shape that limits a polygon. A polygon is limited by a circle. It's one of the ways we can understand the concept of a limit. Now, what he was able to do is to estimate pi to an accuracy of 2 decimal places. He had a lower bound. He had a polygon with 96 sides by the time he was done, and he did that inside and he did that outside. Excuse my drawing. And he was able to get it accurate to 2 decimal places, that the inside polygon and the outside polygon were both 3.14 something something something. That's pretty good. Now, the other thing that we draw from this is that he did 2 things, actually. He took an outer limit, that's the bigger polygon, and said the real value is less than that. And he also took an inner value, this inner polygon, and he said the real value is more than that. So this is where we get the concept of finding a limit from 2 different directions, and where they converge is the estimate, the value that we are actually interested in. To apply the concept of limits to our estimation of instantaneous rate of change, let's say we wanted the instantaneous rate of change at x equals 2. Well, so far we know that we can take a secant, so we could have point P here, and point Q could be at 1, and we'd have a secant, but that wouldn't be very accurate. We'd be more accurate as we pulled this closer and closer and closer to P. So we can find the limit that is as close as possible to the tangent, a secant as close as possible to the tangent, by making this interval smaller, bringing Q closer and closer and closer to P. Now that is finding the limit from the left. But we can also approach point P from the right. We could start at the interval from 2 to 3. Well, that wouldn't be that accurate, so we can bring this point closer and closer and closer and closer, and we would approach the instantaneous rate of change from the right. Now, if we do it from the left and we do it from the right, and we find the limit in between those, then we've found a really good estimate for the instantaneous rate of change. This little discussion is summarized in what we call left-hand limits. Left-hand limits and right-hand limits. Right-hand limits. Now, a left-hand limit uses values that are smaller than or to the left of the value being approached. So values less than the value being approached. So to approach, P from the left would be to use 1 or 1.9 or 1.99 or 1.999 as our second x value. A right-hand limit involves values greater than the value being approached. Okay, so we have left-hand limits and right-hand limits. And either case, the value is very close to the approached value. So just like Archimedes figured out that the circle is the limiting shape of the polygon, as the number of sides gets greater, the side lengths get smaller, the polygon reaches its limit. It reaches the maximum possible area that it could encompass without actually becoming a circle, because a polygon can't be a circle. That's what we mean when we say circle is the limiting shape of the polygon. It's something it can approach but never become. And so he could approach the true value of pi and never attain it using this method, but he would get a very good estimate. In the same way, we can always approach our instantaneous rate of change from the left or from the right by using smaller and smaller and smaller intervals. And we've already done that, but in this lesson, we gain some new language to talk about it. Okay, so in order to successfully talk about limits, we need to meet some criteria. Limits only exist in certain situations, or I should say they don't exist in certain situations. So a limit, or the limit, and we're learning some symbolism here too. The limit, denoted lim of f of x as x approaches a, exists if, and all three of these criteria need to be met. 1, the limit of f of x as x approaches a from the left exists. This should be up on the top line here. Exists. The limit of f of x as x approaches a from the right, so from the positive, from the greater side, exists. And these two right here is what we call our left-hand limit and our right-hand limit. And the third criteria is that these two limits are the same. So the limit of f of x as x approaches a from the left is equal to the limit of f of x as x approaches a from the right. So we're approaching from the left, and there is a limit. And we're approaching from the right, and there is a limit, and they're the same value, the limit from the right and the limit from the left. And if that is true, then we can find the limit. What does that mean? Well, it means that if we have a discontinuous graph, or for instance, some form of a rational graph, we can't calculate the limit from the right here and the limit from the left because it doesn't exist, okay? And because they're not equal. One goes to negative infinity, one goes to positive infinity. So the function then also needs to be continuous at the number that we're working with. So the limit, we're going to write another little definition here. It says a function is continuous at a number, let's say x equals a, if the following three conditions are satisfied. F of a is defined. Okay, so it's not an asymptote or a gap or anything like that. 2, the limit of f of x as x approaches a exists. And remember, that has to approach from the left and from the right, and they have to be the same limit. And the limit of f of x as x approaches a is equal to the value of the function at a. So the value of the function at a is equal to the value of the function of x as x approaches a. So as x gets closer and closer and closer to a, and we estimate that limit, it's limited by the actual value of the function at a. Okay, what does that mean? That means that you can't approach from one side and kind of be approaching this value, and then actually it stops here and picks up going just straight across or something like that. Okay, that can't happen. It needs to be continuous, as in, I mean, graphically, it's pretty easy to understand. That's continuous, okay? As we approach from the left and from the right, the limit exists. It's there. It's not undefined. It's a solid point. And the limit heading from this way and the limit heading from the right actually equals the value of the function at that point. Okay, that's all that's saying. So again, this is a continuous graph. This is discontinuous. And this one has a discontinuity. So neither of these are continuous. They might be continuous at a given point, but the graph overall is not continuous. This one, however, represents a continuous graph for all values of x from the set of real numbers. Example 1, we're going to apply limits to analyze end behavior of a sequence. So we're going to do this with two different sequences. First, we're going to state the limit if it exists. If it doesn't exist, we're going to explain why. And second, we're going to write a limit expression to represent the end behavior of the sequence. The first sequence that we're going to deal with is 1/3, comma, 1, comma, 3, comma, 9, comma, 27, comma, dot, 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 comma, 3 to the power of n minus 2, 3 to the power of n minus 1, 3 to the power of n. Okay, this is our sequence. Now right away I'll tell you this sequence does not have a limit. Okay, it is continually, the value of each successive term is continually increasing. It's not converging to a specific point or to a specific value. If we were going to graph this, this would just go forever and ever and ever. So to plot all these points and draw a smooth curve, we'd end up with something like that, okay? So for 1, this has no limit. Why? Terms are increasing and do not converge. Okay? Now, to write a limit expression to represent the end behavior, so we've got this end behavior, which we know it's going forever and ever and ever. Basically, what we're going to say is that we are looking at, for number 2, the limit of our function, 3 to the power of n minus 2, as n approaches infinity. Right? So here's n, the term number, okay? And n is going to go on and on and on and on and on. And as n approaches infinity, we just put in higher and higher and higher values for n. What happens to the value of the function itself? Well, it also approaches infinity, okay? Basically, this just indicates that the value of each term is getting larger and larger positive values. It's increasing without bound, so the limit does not exist. The second sequence that we're going to deal with is 1/2, 2/3, 3/4, 4/5, 5/6, and it keeps going to n over n plus 1, and keeps going. Okay. Well, let's examine this one. We could convert each term to a decimal, and then we could see maybe more easily that these terms are continually increasing, but they're not increasing without bound. They're approaching a specific value. So 1/2 is, I'm just going to rewrite the sequence using decimals so we can see this. That's 0.5. This is 0.66 repeating. This is 0.75. 4/5 is 0.8. 5/6 is 0.83. And 6/7, etc. You could keep on going. And you can see that at first there's a pretty big jump between terms, but that jump gets smaller and smaller and smaller. And well, let's write the next 3 terms even. We've got 0.857, 0.875, 0.889, and it keeps on going. And so it looks like they're reaching their boundary. Here we have 0.8, then 8.83, then 0.86, then 0.88, then 0.89, okay? They're increasing less and less every time. If we wanted to double check the bound, you could kind of guess. You might say this is approaching 0.9. If you look at this and, you know, n is getting infinitely bigger and the denominator is 1 bigger than that, well, you should be able to kind of see that this is approaching 1. And one way to test that is to take a really large value of n for the last term in the sequence, represented by n over n plus 1. So if we subbed in t of 1,000, let's say, we would end up with 1,000 over 1,000 plus 1, 1,001. And we would get 0.999. Okay, so it's going to get closer and closer and closer to 1, but it's never going to reach 1 because the value of the numerator is always 1 less than the value of the denominator. So let's come up with an expression to say that, okay? We're going to take the limit of end behaviors, that's as x approaches infinity, of our function, which is n over n plus 1. And that is equal to, the limit is 1. The value of this function is going to get closer and closer and closer. The value of this sequence, the terms in the sequence is going to get closer and closer and closer to 1 without ever actually reaching 1. 1 is its limit, and here's how we note that. Example 2, we are going to analyze a graph to evaluate the limit of a function. So we can do it with a sequence. We can also do it with a continuous graph. Okay, so in this case, we're just going to look at the graph and make some evaluations about it. Okay, so what are we going to do? We're going to look at the left-hand limit as x approaches 4 from the left, right-hand limit as x approaches 4 from the right. Then we're going to say, okay, where do these two limits converge? Because it's continuous at x equals 4. That's going to be our limit as f of x approaches, limit of f of x as x approaches 4. And then we're going to calculate the value of the function at 4. Okay, so here we go. again, this refers to the limit of f of x at 4 as we approach 4 from the left. So 4 in your picture, if you're following along in the textbook, that's probably best. We're on page 28. But basically, we're going to follow this curve up from the left. And we're going to say, okay, what's the y value that we're approaching as x approaches 4? And the y value that we are approaching is -2. So as x approaches 4, y approaches, 4 from the left, y approaches -2. You could even say something like from below. And now we're going to take the right-hand limit. So we're going to come from the values that are greater than 4, from right to left. We're going to come down this slope toward 4. And as we approach 4 from the right, as x approaches 4 from the right, y approaches again, -2, this time from above. Okay? Now we're going to look at the limit of f of x as x approaches 4, and all we need to do there is say, well, the left-hand limit and the right-hand limit are both -2, so, and also the conditions for continuity are satisfied. There's no discontinuity at x equals 4. Therefore, f of x is continuous at x equals -2. So the limit of f of x as x approaches 4 is equal to -2. And just by looking at the graph, we don't know the equation. The value of f of -4, the value of f of x when x is 4 is -2. So in this case, we're just seeing from the graph that if we didn't have a graph, but we had the equation, and we could find the limit from the left and the limit from the right, and they converge, then we can also know the value of that function at that point, okay? Your practice problems are from page 29, numbers 1 through 16, but 16 just do A.